All right, this video is a little longer than usual, so I'm going to keep this intro really short. I'm going to start off showing some common mistakes that most beginners make when they're TIG welding or learning to TIG weld. Then I've got about 17 short topics: carbon steel, stainless steel, and aluminum. Let's do it. A common mistake beginners make is not cleaning their metal. Sometimes mill scale is really thick, sometimes it's kind of thin. In this case, it's a pretty thick coating and it's just not doing well at all. It's sparkling, it's spitting and spewing. It's just hard to get good results welding over hot rolled mill scale. It's not much fun, and it's not even good practice because it's not a good representation of what's going on. Well, let's clean that off just using a grinder. Now we're down to clean, bright metal. The puddle wants to move so much easier. It flows at lower amperage, and all of a sudden TIG welding is more fun again. But if we take it a step further, make sure the metal's clean, make sure we got a nice cup on there like a Jazzy 10, and we get even better results. Another mistake people that are learning to TIG weld do oftentimes is use too long of an arc length. We'll show that in a minute and what it does, but first let's show a correct arc length, or one that is somewhat correct. Generally speaking, you want your arc length to be the diameter of your electrode or slightly less. What I mean by arc length is the distance from the tip of the electrode to the puddle. So you want that to be just about the same as your electrode diameter. Now let's take a look at a long arc. So for this little bead here, I set the amperage to kind of a minimum amperage where I can run a bead, but if I hold a long arc, it makes a huge difference. 79 amps on 1/8 inch thick material is kind of low. So it's running a bead fine here, but when I lengthen the arc, you can see it just quits moving the puddle. And then the arc plume is big. It makes the hot tip of the rod blob in the puddle. If I tighten that arc length back up, everything gets better again. Sharp electrodes weld better. Welding with a crapped up electrode is no fun. This is an extreme example. I just flicked some metal onto the electrode and it's creating a big haze and the arc is inconsistent. And sure, it's welding, but again, not fun, not good. Another common mistake happens when you're preparing your tungsten, when you're cutting and sharpening it. So a lot of people snap their tungsten like that, and you can get a split in it like that. And when you get a split, it usually acts up on AC a lot worse than it does on DC. You're a lot less likely to get a split in your electrode if you score it first, almost all the way through where it snaps really easily. When you're sharpening your electrode, you want to have all your scratches running lengthwise. I've done this a lot in a pinch, but for best practice, for best results, and for best arc starts, especially at low amperage, you won't get that if you have your scratches running lengthwise. Rough scratches and scratches that are running sideways can give you poor arc starts, and you might even make you melt a cooling fan off or something that you didn't intend to arc off on. If you have to use a hard rock like this that's kind of rough, at least get your scratches running lengthwise. Of course, best practice is to use a tungsten sharpener with a diamond wheel. It's nice and smooth and get a nice, good, prepared tip. Not everybody can afford a tungsten sharpener. Well, that was a lot of common mistakes. Now let's move on to some skill exercises and learning to TIG weld better. Something I think every beginner should do is pad beads on steel and aluminum. We'll do both here. Padding beads means trying to overlay a bead halfway over the previous bead as uniformly as you can. This does not have to be on flat metal. If you've got some round stock, you can get creative. You can pad beads on most anything. The metal does need to be clean. I had this piece of round stock in one of my buckets, my scrap buckets in the shop. I decided to pad beads on it to make it look like one of those log art pieces, like a paperweight or something like that. A lot of practice. That's a lot of beads, a lot of practice, very efficient hood time. Something I learned training TIG welders years ago was if I could get them alternating between carbon steel and aluminum, back and forth, it really sped up the learning curve and kept them focused, kept them on their toes, and also helped keep them from falling into a rut or a plateau. I've got this amperage set here fairly low for 1/4 inch steel at 118 amps, and the reason for that is if I do hold too long of an arc here, it'll tell me. If I pump it up to 125 or so, it's too forgiving. So I'm running it fairly cold, and I think that's good practice when you're padding beads, to try to use kind of minimal heat. an amperage setting that won't allow you to hold too long of an arc. Now you don't have to switch every single bead over to aluminum, but every 2 or 3 beads, switching back and forth from AC to DC, from aluminum to steel, and back and forth, really helps. Flipping a switch is all it takes on this machine to go from DC to AC, once you have your AC balance and frequency set. This is also a really good opportunity for you to experiment with your ripple spacing. And your ripple spacing is largely determined by how frequently you add filler wire, or how far ahead you move ahead with the torch in between dabs of filler metal. Experiment with that and find what works for you. If you're finding that you're dipping your tungsten too much and you're having to spend too much time cutting off tips of electrodes and re-prepping them, try this technique. This is something that I learned and really has helped me in a lot of cases. I'm lengthening my arc while I add filler metal. When I add filler metal, the height of the puddle grows. Sometimes it grows right into the tip of the electrode, and so this prevents that from happening. It keeps me from having to clean a lot of electrodes. Just one way of doing things. Switching back and forth gives one piece time to cool off, and is a whole lot of good practice with very minimal metal and very minimal prep time. All right, now let's take a look at an outside corner joint 11 gauge cold rolled steel. Padding beads kind of really prepares you for doing this, because you're really not doing much different than you would be just running a bead on steel. But you are having to keep an eye on your arc length, and also you're having to keep an eye on those corners to make sure you don't melt them too much. And then of course when you get to the end, you will taper amperage back up a little bit to prevent melting the end away, or to prevent leaving a crater hole. Pulse settings are a super nice feature to have, not 100% necessary most of the time, just nice to have. I did a project a while back, and it was a stainless steel cooling manifold. And I found that using the pulse settings on this machine really helped to speed up travel speed and also reduce heat input. Using 1 pulse per second with a fairly low background current of only 20%, it really did limit heat input and actually sped up travel speed, and I limited discoloration as well, even though I was only using about a number 8 gas lens here. Let's take a look at using a Jazzy 10 ceramic cup on some stainless coped tubing. This has a double layer diffuser screen in there. When you combine that with the diffuser screens that are already in the adapter kit, you really got something. You can push argon out a long ways, so when you need to use a long stick out, you can still get a really good blanket of coverage. Something really important on a stainless weld like this is to get that puddle established really quickly and get moving really quickly. About 3 seconds maximum. 2 seconds is even better. Otherwise, heat can build up so much that it's difficult to outrun it. Sometimes you need to use a longer stick out, so a little bit larger cup comes in handy. I'm going to use the Furic Clear 12 on this coped steel joint. And the only reason I really need a long stick out here is just to get the cup out of the way of the camera, so that you can see the tip of the electrode, the arc shot, the way the puddle's flowing, and things like that. But it's a really good cup for coped steel joints, cluster joints on chromoly, and stainless steel. Let's switch gears now and take a look at a small aluminum project. A really small project. This is just a business card holder. The idea behind this is something to hold your business cards and give this to a potential customer to kind of showcase your ability to weld. I'm using a number 8 clear cup on this weld, and it's really lighting things up. Sometimes you can even look through that cup when you get into a corner, or any other odd angle, welding away from yourself. But I think the main benefit of a clear cup is just that it really does kind of act like a light bulb with a tungsten filament up inside there, and it just kind of lights the whole area up around it, and you can see where you're going better, you can see the joint better, you can see the puddle better. And when you go back to a pink cup, it really is like somebody dimming the lights, so it makes a big difference on how well you can see. I'm about to make a big, fat, wide bead, and so I'm lowering the AC frequency to about 50 Hertz, and I'm cranking the amperage up to max, because I want to make a really wide bead and cover this whole joint up with one bead and wrap those corners. And low frequency, to me, really helps in doing that. I like using higher frequencies, but when I'm limited to a 200 amp machine like this one, I can get more heat out of that machine at lower frequencies for thicker aluminum like this. Now if you've got a big Dynasty 400, you can go with 250 Hertz if you want and still melt thicker metal. But I've only got 200 amps here. Let's take a look at a 5F weld test, an aluminum tube to plate. This weld test is given sometimes to qualify strictly for fillet welds, socket welds in all positions. The main goal is not a stack of dimes. The main goal is to punch it into the root so that when they do the macro test and the bend break test, you don't want to have any lack of fusion in the root. So that takes a tight arc. It takes waiting enough time between moving the torch ahead to allow that puddle to wet into that root of the joint. Of course you want the appearance to be uniform and to be acceptable, but a stack of dimes is not the goal. A macro etch test, also called a cut and etch test, is a really good learning tool, especially on a video like this when you can correlate the arc shot, the front of that puddle, the leading edge of that puddle, with the end result. One test is worth 100 opinions. We already looked at a corner joint, but now we're going to compare a continuous current to pulse settings. And since we already did one, I'll just show the very end of this one, tapering off amperage on the end of the corner and then backing in as amperage is tapered. When you turn the pulse on and use pulse settings, you often have to go higher on the amperage because you're getting an average of the low pulse and the high pulse. We're going to use roughly 2 pulses a second here with a background current of 30%. For this joint, I stepped up to a larger filler wire size, a 332, and just left the rod in the puddle. That can really limit the heat and really prevent discoloration on a stainless joint. Even though this is carbon steel, you can see that it's really limiting any discoloration. It's putting less heat into the part. And of course that Furic Ceramic 12 is helping a bunch too. I've found those same pulse settings that I just used work really well for TIG brazing with silicon bronze. Pulse settings seem to really help with silicon bronze, and so does a number 12 cup like this Furic 12. The pulse keeps the heat down and the large argon envelope keeps that puddle clean. And of course your metal needs to be really clean too. We're going to take a look now at a chromoly cluster joint. This is 120 thousandths wall thickness, 2-inch tube. Going to use a Jazzy number 10 with about 20 CFH to start with. This is a 2-pass weld. That first pass is done just with continuous current, a nice tight arc. Make sure to get good penetration as far as you can down into the root of that joint. Then we'll let it cool and come over top of these beads with a second pass. We'll do just a little bit of pulsing with the foot pedal on that second pass. I'm not coming all the way off of that foot pedal, just enough to let the puddle cool just a little bit and make a distinct ripple. I didn't use any preheat on that, but this is 1-inch thick chromoly coming up here. We definitely need a preheat on that, around 500 degrees Fahrenheit. You got to slow the cooling rate down or you can have brittle welds. I'm also using ER70S2 filler here. And even with that 500 degree preheat, the Furic Ceramic 12 gives me a silver weld. Really good coverage. Up next is an 1/8 inch thick carbon steel lap joint. I'm going to be using a number 8 clear cup on this joint, mainly because it's going to light up everything and provides a better video. Gives a better arc shot, and it lights up where I've been, where I'm going. It lights up the tip of the tungsten. It really is kind of like a light bulb. I'm using about 105 amps here. I'm really watching that top toe of that weld to just consume that corner of that lip. This is 1/16 diameter ER70S6. That stuff flows pretty nice. I have saved and accumulated lots of aluminum plates, and I keep them in a bucket in the shop for using for chill bars like this. This is 18 gauge cold rolled steel, and the more you can chill that stuff, the less distortion you'll have. Another side benefit is not much discoloration. So if that's important to the job you're doing, like if this was thin stainless, that would be hugely important. Chill bars make a huge difference. You can't always use them. Sometimes the shape of the part doesn't permit, but when you can, they really make a difference. I rarely use a number 4 cup, but I do sometimes when I want to save gas, and also for flash tacking. This machine's got a remote and panel button on it, and even when I've got the foot pedal plugged in, if I put this on remote, the foot pedal turns into a switch, just an on-off switch with no amperage control. So I'll set the machine hotter than what I would normally weld at, a lot of times 1.5, sometimes even twice as hot as I would normally weld at. I'll set the tungsten where it's just barely sticking out the end of the cup, and with a number 4 cup, that only takes about between 5 and 10 CFH, not even. Then I will prop the cup right on the metal, and generally speaking, I will rock the tip in until I can feel it touch, and then just rock it back just a little bit, and then tap the foot pedal very quickly. I would strongly advise you to practice on some scrap metal before you start doing this on actual parts, but it's just a really quick way to get some spot tacks on something. Alright, let's take a look at some pulse settings for TIG brazing with silicon bronze on a lap joint. This is strictly ornamental stuff, just playing around. Silicon bronze filler metal is not nearly as strong as ER70S2 or 6. Not as strong, but it's really good for temporary fixtures. It's good for fixing a worn place in a thin hydraulic tube or something like that. But I'm just playing around with pulse settings right here. Moving ahead during the high part of that pulse, and then pausing during the low amperage part of the pulse. The pulse seems to really help keep the filler metal cooled off and keep it from getting too heavily oxidized. And of course that 12 cup is keeping everything shielded too. Here's an 063 wall 4130 tubing cluster joint. My amperage is reading somewhere between 62 and 65. There's a rule of thumb that says 1 amp per 1,000ths of thickness. That doesn't always hold completely true, but it's holding pretty true right here. It really seems to go squirrely when you get thicker than 1/8 of an inch. But right now I'm holding about 62 amps on 063 wall material. It's about right. This is ER70S-2 filler metal. A pretty common filler metal for 4130 chromoly. The last weld I'm going to show here is an overhead socket weld. This is 2-inch socket weld. My friend Andrew Carden is doing the welding here. He's burning this first pass in here at 196 amps to really punch in that root. I think really 140 would have still done the job, but we're just kind of experimenting. Second pass is at 125 amps because the piece is already good and warmed up. And the second pass moves along just a little bit slower with a little bit of a weave action. This is going to be a 3-pass weld. Oftentimes inspectors want you to fill that weld up all the way to the shoulder of the fitting. But if you do it pass after pass without ever letting it cool, it'll get too hot. So we let it cool between passes, wire brushed it really good. This is the third and last pass, completely filling it up to where there's no undercut, no chopped off edges of the fitting. This was done all freehand. You could also walk the cup. You know I like to test things, so we did a cross-section cut and etch on this piece just to verify what we thought was good penetration into that root. A quick swab etch with some nidal etch shows the weld profile, and we can quickly re-watch the root pass here, and then we can quickly correlate the level of penetration we got on the root pass there on the cut and etch test. A very valuable learning tool. Hey, I support these videos with my online store at weldmonger.com. If you'd like to learn more about any of the products I use in this video today, just go to weldmonger.com. Thanks for watching.